Yes, thank you. Thank you for the invitation. Very happy to be here. I represent IFE, which is a research institute working on energy technology. We are based in Kjeller and Halden. So today I will talk about how to treat organic waste and residues and generate valuable bio-based fuels and products out of it. Energy also, and how to create value also. So I will go briefly through the context and the challenges the cities are facing with waste. Defining waste and residues which are causing problem to these cities. How we can solve the problem and create value, and choose two examples, the biogas value chain and the solid waste incineration that was mentioned by Jannike at the moment. I will try to give you also an insight of how we can close the loop using CO2. Is it working?
Yes, it's working. Just take it closer.
Close enough. It's better now? Yeah. Okay. Yeah, so the context is that we have growing urban areas. This is for sure. And about 60% of the population will live in urban areas by 2050. And 90% of the increase is going to take place in Asia and Africa, so not in developed countries. So we all agree that the sustainable urbanization is key to solve this issue. And many countries are facing actually these problems in growing cities: housing, transportation, energy systems, and other infrastructures like waste handling, which I'm going to focus on. So the idea here is that waste handling in urban areas has to be part of the solution. So which waste are we talking about? In cities, basically, you have liquid waste, which are sewage, wastewaters, and solid waste that we define as MSW, municipal solid waste. Some of these waste are sorted out, and we try to recycle, and the rest we have to get rid of it in a smart way. There is a comparison between EU and China. You see that what is dominant is food waste, paper, plastics, glass, metals. You have also waste produced from nearby industries, close to cities. That's typically food, beverage, agricultural industries. So how to solve the problem and try to create value? Well, we agree that we have to meet sustainability, and we have to avoid landfilling. Landfilling can cause pollution to ground and water, and this we want to avoid. It's also important to reduce the carbon footprint. We've heard that today many times, and emissions to air, among others, NOx, and try to create value. So there is one clear option which has been pointed out today several times. This is what is called the waste to energy approach, because it means all these requirements. You can produce heat and electricity for households. You can produce biofuels for transportation or other clean fuels. And you can also produce byproducts by recycling and reuse of mostly carbon. That's carbon which is boosting our cities, by the way. Yeah, and the challenge is to put in place a proper waste collection system and sorting system. So the first example I'm going to tackle today is the biogas value chain. Biogas is produced in a closed system in a so-called anaerobic digester, which is actually the biodegradation of organic matter in the absence of oxygen. That's the microorganism eating the organic matter. Typical biogas composition is about 60% methane and 40% CO2. And this CO2 is mostly bio-CO₂, if it's only organic matter, of course. Biogas is typically produced today from sewage sludge. So the sludge that is recovered after the treatment of wastewater. That's quite big quantities for big cities. And food, animal, and agricultural waste. So food waste residues, and what we throw away, manure from animal, or rest from industries where you produce food from animal, and crops, agricultural crops. So we go into detail for this value chain. So you have the digester in the center, and you feed the different waste in the digester, and what you get from it is a raw biogas containing mostly methane and CO2, plus some impurities, and a solid residue that we call digestate. This biogas, you can use it directly. You have to clean a little bit and remove some water, and then you can burn it in so-called combined heat and power installation, where you produce both heat, which is mainly hot water for district heating, and electricity. The most common way is to use so-called gas engines. So it's a bit bigger engines than what you have in your car, but it's the same principle. Coupled to an alternator to produce electricity. And recently, fuel cells have been pointed out as a very good option because their efficiency is much higher, 50% compared to 35 approximately for 35-40% for gas engine. Then this biogas, you can upgrade it and increase its value. If you increase its value, you have to remove what doesn't have too much value at first, at least. That's the CO2 and impurities. And then you're left with what we call biomethane, which is 97% methane. And this biomethane nowadays is either put in the grid in countries where you have gas grid, and then it's distributed to different users to use this green fuel, or as a fuel directly for transportation, for cars or buses, and now recently for trucks. On the way to this, you can either use it compressed or liquefied to reduce the volume. The digestate is nowadays used for fertilizers, basically, and soil amendments. Biomethane production is increasing dramatically, I would say, in the EU. You see here from 2011 to 2016. And we are exploiting just 10% of the possibilities we have. This is for sure that from cities, it's a bit limited, but it can be expanded around cities also to other types of organic residues. But there are also other uses of biomethane or biogas. Of course, the first approach is to substitute natural gas, which is fossil, and the CO2 emissions from this natural gas are harmful for the environment. And then doing that, you reduce the carbon footprint. So if you do so, all the products produced from natural gas reduce the carbon footprint. But one of the products from natural gas is hydrogen, which is used as a chemical in many industries, and it's also a green fuel, a very clean fuel. So by converting this biogas or the biomethane to hydrogen, we can contribute to produce green hydrogen as clean fuel, and contribute to the early decentralized implementation of this market, which is, I would say, unfortunately, a little bit competing with the battery market for vehicles. So the first application is, of course, for transportation, for fuel cell electric vehicles, or even buses. The advantage of doing so is that you increase the efficiency, because the the fuel cells have much higher efficiency than gas engine. We increase it by 10 to 15%, and you also reduce NOx, which is very often a problem which is not mentioned too much in cities, but which is a problem. It's not only CO2. So this is a clear option for another use of biogas, and it's moving at the moment around this. How to do so? To convert biogas to hydrogen, we use the reforming route. It's a route where you need first to clean up the gas and upgrade, as I mentioned, to remove the CO2 and the impurities. And then there is the so-called reforming step, which is the conversion of methane to what we call syngas, which is a mixture of hydrogen and carbon oxide. This carbon oxide is further transformed to more hydrogen and CO2 inevitably through the shift reaction. And then the hydrogen and CO2 are separated to produce both hydrogen as clean fuel and this CO2. This CO2 is bio-CO₂, and it has a value, as I will show you later. Another way to really utilize everything from the waste in the biogas value chain is to handle this digestate, the solid residue you have from the digester itself. And here, the common route is to use the pyrolysis route. You can also use gasification, but pyrolysis is interesting because you obtain from this step three phases, I would say. One gas phase, which can be processed the same way as the methane phase, produce hydrogen and bio-CO₂. A bio-oil, which is very similar to the fossil oil we exploit today. By cracking it, you can produce liquid biofuels, which are very similar to the biodiesel or even biogas or gasoline we are using today. And there is also another solid fraction, which is the biochar, which is used today as fertilizer, and also carbon fixator in soils. Then the other example I would like to tackle today is the solid waste incineration that was mentioned by Janneke. We are about 450 incineration plants in Europe, and they generate a lot of CO2. So of course, you can capture the CO2 if you want to be carbon negative, but you can also reuse this carbon. And one way of using this carbon is to combine it with renewable hydrogen to produce chemicals. And two chemicals of choice are either methane or methanol. It goes through the methanation step, which is the reverse reaction of reforming, actually. You combining CO2 and renewable hydrogen produced from excess renewable power, of course, to produce methane as chemical. And once again, this methane can be used as a substitute of natural gas to produce produce products which are which doesn't release fossil CO2. Then to finish here, to give you a kind of overview of my message is that by using the bio-CO₂, which is either produced in the biogas chain or in the solid waste incineration, we can close the loop. One concept is, and we can do that in a sustainable way and create value. You can run the concept which is called food to waste to food by reusing the CO2 in greenhouses, for example. And you can also do that in plastic to waste to plastics by capturing the CO2 from incinerator, combining it with hydrogen through methanation, and use the methane to reproduce plastics, which are green in that case. The challenge is, of course, to build a value chain and also to reduce the cost of the technologies. So briefly, just to finish, if you allow me, I'd like to show you what we do at IFE related to this field. We have developed a hydrogen production process from biogas with CO2 capture to extract this bio-CO₂ also as a valuable product. It has potential to reduce cost of the reforming technology by about 20% due to process intensification. We do research also on production of biomethanol from biomass, combining gasification and this process. And biomethanol can be used to produce a lot of chemicals like bioplastics, for example. And also enhanced methanation, because the methanation process which is available today is not very efficient and needs improvement and cost reductions. Thank you.